The denominator for the sample variance given on page 176 is n minus 1. The denominator for the population variance given on page 178 is n. Why is the sample variance n minus 1 and the population variance n? The reason for this is that the sample variance is an attempt to get what is called an unbiased estimator. An unbiased estimator is one where if every possible sample of a given size is taken from a specified population, the average value for all samples, for in this case the variance, would be equal exactly to the true population variance. Let's look at this question of an unbiased estimator, and let's do it for a very small population, small enough that we can actually take every possible sample of a given size. The population will consist of only 4 elements, and the values assigned to these 4 elements are 2, 4, 5, and 7. Let's first look at the mean of that population. It's equal to equal average and it is 4.5. Now, using the function for the population variance given by Excel, which is VARP, we will calculate the variance for this population, and the variance is 3.25. This is 3.25 using the VARP, or population variance formula. If we had used equal VAR, which is the sample variance formula, or the formula given on page 176, we would have gotten the value of 4.3. In general, the sample variance calculated with VAR will always be larger than the true population variance. But we're not going to use the sample variance, we're going to use the population variance. Now, if we have a population of 4 elements, 2, 4, 5, and 7, and we want to take every possible sample of a given size, and the given size we're going to choose is 2, we have the number of elements in the population raised to the power of the number of observations in the sample as the total number of possible samples. We have 4 elements in the population raised to 2 because we're going to take samples 2 at a time, which means we have 4 squared, or 16 possible samples. So I'm going to number the samples right here down to 16, and I'll begin with the first sample. It will have a 2 in the first observation because 2 is going to appear first in every one of the samples. I'll copy this and paste it here, and those are the first 4 samples of size 2. 2 and a 2, 2 and a 4, 2 and a 5, 2 and a 7. You'll notice that when I draw the sample, I'm drawing the sample with what is called replacement. That is, if I draw 2 on the first draw, I still have the opportunity of drawing 2 on the second draw. The second set of first numbers will be 4. And again, each one of these will go with those. And I might as well just paste these on down. This will be 5. And at this point, it will be 7. So here is every possible sample of size 2 taken with replacement from this population. There are no other possible samples, and this is all of them. Here we're going to calculate the mean of the samples. So this will be equal to average of these values. And I will copy that all the way down. And now, to show what is meant by an unbiased estimator, if I do equal average of these values, I get 4.5. So the mean of the means of all possible samples of size 2 taken from this population of 4 is equal exactly to the true population mean. That is what is known as an unbiased estimator. What about the variance? We're going to calculate the variance using the sample variance formula, or the sample variance function, which is equal to VAR without the P of the first and second value. And in this case the variance is 0 because these two values are exactly the same. If I click this down, I now have the variance for each of the samples. Now, what is the average of those variances? It is 3.25, which is exactly the same as the population variance. But note that the population variance was calculated with VARP. The sample variances were calculated with VAR. And this is the average of all of the sample variances. That is an unbiased estimator, and that is why the variance for samples is divided by n-1 rather than n. And while this is only a demonstration of a very small population, taking very small samples, this demonstration would work with any population size and any specific sample size. But as the population gets larger and the sample sizes get larger, this becomes virtually impossible to do in any finite amount of time.